Today, we studied these two topics. In section 4.6, I want to show you two more examples. These two examples are about applications of linear approximation. Then in section 4.7, we will study how to use derivatives to compute difficult limits. Take a review. Review 1. The formula of linear approximation is this. About this formula, the left-hand side is a curve. Right-hand side is the tangent line to that curve at the point A. When the points X and A, they are close to each other, this approximation is very good, very good. Review number 2. This review is for section 4.7. To find a limit, we have three methods. A, we can use a table to find a limit. B, we can plot the graph of the function f, then tell the limit. C, we can use limit laws. Say, limit laws. A limit of a sum is sum of limits. Limit of a product is product of limits. Limit of a quotient is quotient of limits. Those are limit laws. And also we can use direct substitution to find the limit. Directly plug in A in X, then tell the limit. Among these three methods, direct substitution is the most popular one and also the most convenient method to find a limit. Okay, now topic 1, use linear approximation. Okay, two more examples. Example 1, use the formula of linear approximation. Use the formula to approximate the change in the volume of a sphere when its radius changes from 5 to 5.1. Yeah. And here we are given the volume formula of a sphere. The change in volume from 5 to 5.1 is this difference. Volume and R is 5.1 minus volume and R is 5. The difference is the change. Now we need to approximate this change by using this formula. To use this formula, we need to determine the function. What is the function? And we need to determine X, the point, and the point A, Okay, now for the function f, we choose volume. Volume depends on R, so volume is a function of R. Volume is a function. So for f, we choose V of R as f, as the function f. Now for the point X, we choose 5.1 for X and 5 for A. Now plug in this information into the formula, then we get volume at 5.1 is about approximately equal to volume at 5, f of A, volume at 5. Then derivative at 5 times X minus A, 5.1 minus 5. Move V of 5 to the left-hand side, then we get this approximation. Okay, now let's compute derivative. Okay. Yeah. Take derivative on the volume with respect to R. then we get derivative is 4 pi r squared. Plug in 5 in r, then we get derivative at 5. It is 100 pi. Now, put this number here, plug in this number here. Then we get the difference. The difference is about 100 pi times 5.1 minus 5. It is 10 pi. 10 pi. So therefore, the change in the volume when the radius changes from 5 to 5.1 is about 10 times pi. 10 times pi. Example 2. The radius of a sphere was measured and found to be 21 cm, with a possible error in measurement of at most 0.05 cm. Here I use RM to denote the number 21. M means the measured value. A possible error in measurement of at most 0.05 means this inequality. RT. By RT, I mean the true value of the radius. Usually, we don't know it. We don't know the true value of the radius, usually. Okay. The difference between the true value of the radius and the measured value of the radius in absolute value is not greater than 0.05. This is what this sentence means. Okay, now we have two questions. Question A, what is the maximum error in using this value 21 of the radius to compute the volume of the sphere? That means that we need to estimate the volume computed by Rm and the volume computed by the true value of the radius. Volume computed by the true value of the radius is the exact value of the volume. We need to estimate the difference between these two quantities. This is question A. Question A. Now, question B. Estimate the percentage in the volume calculation in question A. In question A. Now, let me answer question A. Question A. We need to estimate this quantity. This quantity, absolute value of the difference between the exact volume and the volume computed by the measured value of the radius 21. I use the linear approximation formula to estimate this quantity. In this formula, we need to determine function f and the point x and the point a. For function f, I set function f to be the volume. Volume depends on R. It is a function. So I set f to be the volume function. And for the point A, I set Rm 21 for the point A. For x, I set the true value of the radius RT for x. For x. Okay. Now, plug in this information into the approximation formula, then we get this approximation. F of x is volume at RT. X is RT. X is RT. So volume at RT, left hand side. F of A is volume at Rm. A is Rm. And then plus derivative at A, derivative at Rm. X minus A, RT minus Rm. Now I move this number to the left side to get this inequality. Take absolute value on the both sides. Now I compute derivative on V and evaluate derivative at Rm. Derivative on V, take derivative on V with respect to R, then we get derivative on V is 4 pi R squared. Plug in Rm in R, then we get this number. Rm is 21, we get this number. Now, put this number in derivative here. Then we get this approximation. From the given, we know that RT minus Rm in absolute value is less than or equal to 0.05. So therefore, use that inequality, then we get this inequality. So this number by calculator is about 277. Okay, now conclusion. The maximum error, the error of the computed volume from the exact volume. The maximum error in using Rm 21 to compute the volume of the sphere is about 277. Yeah. This is our question A. Now question B. Estimate the percentage error of the computed volume from the exact volume. The formula of percentage error is exact value, exact volume minus computed volume over exact volume. Volume at RT we don't know. Yeah. So exact value of the volume of the sphere, we don't know it. Okay. Now, because we don't know this guy, I replace RT by Rm. I know Rm. Rm is 21. So volume at 21 is computable. It is this number. From pi A, V of RT minus V of Rm is not greater than 277. So this quotient is less than this number. Okay, by calculator, this number is 0.0071. In percentage, it is a 0.71%. So the percentage error is not greater than 0.71%. That means that using 21 to compute the volume of the sphere, the result is quite, we are quite confident the result is accurate. Topic number 2. This is a topic in section 4.7. 4.7 is about using derivatives to compute difficult limits. When we compute a limit, usually we use direct substitution. However, direct substitution doesn't always work. When a direct substitution doesn't work, we say that the limit is a difficult limit. Now here we have some examples about difficult limits. Here we have several limits to compute. A, when x approaches 1, what number this quotient will approach? Okay. To find this limit, I try direct substitution. Plug in 1 in x, then I get the limit 1/2. So direct substitution works well. So this limit is an easy limit, not difficult. Now B. When x approaches infinity, what number this function will approach? I directly plug in infinity in x, then I get this. Infinity plus infinity square, it should be infinity. So this limit is also easy to tell. Easy limit, easy limit. Now C, when x approaches positive infinity, what number this function will approach? I try direct substitution. Plug in infinity in x, then I get infinity minus infinity square. Infinity square is infinity. So we have infinity minus infinity. But now infinity minus infinity, what is that? It can be any number depending on the problem. Depending on the problem. Infinity minus a final number, we can tell it is infinity. A final number minus infinity, also easy to tell. It is negative infinity. Now, infinity minus infinity, difficult to tell, difficult to tell. So, about this limit, direct substitution doesn't work. So we say that this is a difficult limit. The book calls this limit an indeterminate. Indeterminate means cannot be determined by direct substitution. The book called this limit an indeterminate limit of the type infinity minus infinity. Now, how to find this limit? Direct substitution doesn't work. We can turn to use a table, yes, but I don't like a table because a table is tedious. Let me rewrite the function so that the function is in a form that is easy to tell the limit. Let me factor x squared out, the highest power. Take x squared out. Then x becomes 1 over x. X squared, when x squared is out, only 1 left. Now plug in infinity in x, then we get this. 1 over infinity is 0. So we have infinity times 0 minus 1. 0 minus 1 is negative 1. Negative 1 times infinity is negative infinity. So this limit is negative infinity. Now the limit in D. When x approaches positive infinity, what number this quotient will approach? Okay, again, I try direct substitution. Plug in infinity in x, then we get this, okay. In the denominator, infinity squared minus 4, it should be infinity. In the numerator, 2 times infinity squared plus infinity minus x, minus 6 should be infinity. That means that when x approaches infinity, denominator approaches infinity, numerator approaches infinity. Now, direct substitution leads to infinity over infinity. What is infinity over infinity? I cannot tell. I cannot tell. I can tell when a finite number divided by infinity, it is 0. Infinity over a finite number, I can tell it is infinity. But infinity over infinity, I cannot tell. It can be any number depending on the problem, So about this limit, direct substitution fails. So this is a difficult limit. The book calls this limit an indeterminate limit of the type infinity over infinity. Then how to find this limit? A table works, but I prefer to rewrite the function. Take out the highest power x squared. Okay, take x squared out, then we get this. Cancel x squared, then we get this. Okay, when x approaches infinity, this term 1 over x will approach infinity, and this will approach 1 over x will approach 0. 6 over x squared will approach 0. 4 over x squared will approach 0. Or you can say that directly plug in infinity in x, then we get this. 1 over infinity, 0. 6 over infinity square, 0. 4 over infinity square, also 0. So 2 plus 0 minus 0 over 1 minus 0. So the limit is 2. Now, the limit in E. When x approaches 1, what number lateral log of x over x minus 1 will approach? Direct substitution, I plug in 1 in x, then I get lateral log of 1 over 1 minus 1. Lateral log of 1 is 0. Now this time, I get 0 over 0. 0 over 0, I cannot determine it. 0 over a finite number, it is 0, I can say. A finite number over 0, it is infinity. But 0 over 0, I don't know what is that. Now this time, direct substitution fails again. So this limit is a difficult limit, cannot be determined by direct substitution. The book calls this limit an indeterminate limit of the type 0 over 0. Then how to find this limit? A table, sure, table works. Simplify the function, but this time it is difficult to simplify the function because lateral log, it is not a polynomial. If lateral log is a polynomial, then I can factor the polynomial, cancel out some factor to simplify the function. So simplify the function, this method doesn't work. Yeah, let me turn back to a table. Yeah, here a table, a table. I use a table to tell the limit. First column, independent variable, x. Second column is numerator. Third column, denominator. The last column is the function, Now, I let x approach 1 by first taking 2 for x. When x is 2, calculator, lateral log of 2 is this number. 2 minus 1, 1. So function value is this. Okay. Then pick 1.5, calculator. Pick 1.1, calculator. Then when x approaches 1, numerator, lateral log of x will approach 0. Will approach 0. See, the top here is 0. X minus 1 will approach 0. Yeah, denominator is 0 here. But the ratio, the function, will approach the number 1. So I say that, so the conclusion is when x approaches 1, this function approaches 1. This is D, okay, D. Now, f, the function in f. Yeah. When x approaches infinity, what number this difference will approach? Direct substitution doesn't work again. Okay. I directly plug in infinity in x, then I get this. Infinity square plus 1, infinity. Take square root on infinity. It is infinity. So we have infinity minus infinity. I cannot tell what is that. Cannot tell. So direct substitution fails again. This is a difficult limit, cannot be determined by direct substitution. The book calls this limit an indeterminate limit of the type infinity minus infinity. Now to find this limit, I rewrite the function. I use algebraic conjugate. Algebraic conjugate, a minus b, then I multiply the top by a plus b. Okay, and also multiply the bottom by a plus b. Okay, a minus b times a plus b is a squared minus b squared. This is a formula. 1 times this guy is this guy. Okay, now simplify the numerator. Then we get numerator is 1. Now this time, when I plug in infinity in x, I can tell the limit. I can tell the limit. The limit is 1 over infinity. It is 0, 0. This is a f. The limit in g. Limit in g. When x approaches 0 from the right side, that means that x is positive. When x approaches 0 from the right side, what number x to x squared will approach? Yeah. Direct substitution, plug in 0 in x, then we get 0 to 0. What is 0 to 0? Any number can be possible, 0 to 0. I cannot determine 0 to 0. I can determine a finite number to 0 is 1. 0 to a finite number, it is 0. But 0 to 0, hard to say, difficult to say. So this limit is a difficult limit, cannot be determined by direct substitution. The book calls this limit an indeterminate limit of the type 0 to 0. Then how to get this limit? This time, use a table. You cannot simplify the function. This function is simple enough. Use a table. Okay, now let me make a summary. A summary about the types of indeterminate limits. Here, indeterminate means cannot be determined by direct substitution. How many times of difficult limits? Okay, 0 over 0, difficult, I cannot tell. Infinity over infinity, I cannot tell, difficult. 0 times infinity, cannot tell. 0 times infinity, any number can be possible. Infinity minus infinity, difficult. 0 to 0, cannot tell. Infinity to 0, I cannot tell. A finite number to 0, say 3 to 0, I can tell. It is 1. But infinity to 0, I cannot tell. And also, I cannot tell 1 to infinity. 1 to, say, a finite number, 1 to 1 million, say for example, I can tell it is 1. But 1 to infinity, any number is possible. So in total, there are so many times of indeterminate limits.